let's talk about LU factorization and LDU factorization. Topics for this week were a bunch of factorizations: LU, LDU, PA equals LU, and LDL transpose factorizations. Those were the topics for this week. Okay, let's do an example. Let's find the LU factorization of this matrix. A equals 2, 2, 4, 0, negative 3, 6, negative 4, negative 7, 3, negative 3. So the LU factorization process starts by reducing the matrix into upper triangular form, which we've done before. So the first step would be to reduce this negative 4 to a 0. So we would want to do row 3 plus 2 row 1 to do that. And you can represent that as an elementary matrix, E31, which is 1, 0, 0, 0, 1, 0, 2, 0, 1. So when you do that operation on the matrix A, you get this new matrix, 2, 2, 4, 0, negative 3, 6, 0, negative 7 plus 4 gives you a negative 3, and negative 3 plus an 8 gives you a 5. Okay, and then we're going to want to reduce this negative 3 to a 0 to get it into upper triangular form. So we can do row 3 minus row 2 in order to get that. So if we do that, well, that operation is represented by this matrix E32, the elementary matrix, 0, negative 1, 1. And then when we do that operation, we get this lower triangular matrix, this upper triangular matrix. So this is U, this is the matrix U in the LU factorization. So what we did is we took A and we multiplied on the left by E32, or sorry, E31 first, and then we multiplied on the left by E32. And that gave us the matrix U. So if we take these matrices and we multiply both sides by the inverse and move them to the right-hand side, and that gives us A equals E32, E31 inverse times U. And so this E32, E31 inverse, that's the lower triangular matrix L. So another way you can write this is, if you remember when you have a product of two matrices and you invert the product, it's the product of the inverses in the reverse order. So you have to swap the order, so this will be E31 inverse E32 inverse times U. So in order to find L, we just have to find the inverses of the elementary matrices and then multiply them together in this order. So if you remember how to find the inverse of an elementary matrix, E31 inverse, you just take the 2 and make it a negative 2. And for E32 inverse, you take that negative 1 and make it a positive 1. So you take For an elementary matrix to find its inverse, you just take whatever entry is different from the identity matrix and change the sign. So we just need to multiply these two matrices together to get L. So L is E3(1) inverse times E3(2) inverse. So when you multiply these two together, you should get this, which is a lower triangular matrix. So in summary, the LU factorization of A is this L matrix times the U matrix from before, which was this one, 2, 2, 4, 0, negative 3, 6, and 0, 0, negative 1. So that's LU. That's the LU factorization. Any questions about that process? Let's use this to solve the system AX equals B. So let's say we want to solve AX equals B using the LU factorization of A, where B is the vector, let's say 2, 3, 1. So we're solving the matrix A, 2, 2, negative, or 2, 2, positive 4, 0, negative 3, 6, negative 4, negative 7, negative 3, times x1, x2, x3 equals B for x. So the LU factorization allows us to do this in 2 steps. So since A is LU, that means that AX equals B becomes, so if you combine these two together, you get LU x equals B. So if you let UX equal this vector Y, UX is a vector, so just call it Y, and then the system LUX equals B becomes LY equals B. So now we have these, we've converted the original equation AX equals B into an upper triangular system, UX equals Y, and a lower triangular system, LY equals B. So we can solve the equation in 2 steps. You can first solve LY equals B for Y, and that would be using forward substitution. And then once we have Y, we can solve UX equals Y for X using backward substitution. So starting with LY equals B, our L matrix from before was this matrix. So we're multiplying by Y, and we're getting B, which is 2, 3, 1. So from this system, we immediately have, from the first equation, y1 equals 2. From the second equation, y2 equals 3. And in the third equation, we get negative 2y1 plus y2 plus y3 equals 1. And so if we solve for y3, we get y3 equals 1 minus y2 plus 2y1, which if we substitute these in here, we get 1 minus 3 plus 2 times 2 for y3, which is equal to 2. So that means that the vector y is equal to 2, 3, 2. So this was like the first step. The second step is solving ux equals y for x. So our U matrix was 2, 2, 4, 0, negative 3, 6, 0, 0, negative 1 times x equals y, which is 2, 3, 2. So the first equation, or I guess we're doing backward substitution in this case, so the last equation gives us negative x3 equals 2, so x3 is negative 2. The second equation says negative 3x2 plus 6x3 is 3. So if you substitute in x3 equals negative 2 into here, you get negative 3x2 plus 6 times negative 2 is 3. So negative 3x2 is equal to 3 plus 12, which is 15, meaning x2 is negative 5. So for the last equation, we get 2x1 plus 2x2 plus 4x3 equals 2. And we can use x3 equals negative 2 and x2 equals negative 5 in this equation to solve for x1. So if you divide everything by 2 in this equation, that'll simplify it a little bit. You get that. So plugging in some numbers, you get this. Solving for x1, you get 1 plus 5 plus 4, which is 10. So x1 is 10. So together, our solution is x equals 10, negative 5, negative 2. That's how you use the LU factorization to solve AX equals B. So in summary, the way you go about the process is you reduce the matrix A using some elementary matrices on the left into an upper triangular matrix. And which means that A is equal to the inverse of the product of all the elementary matrices times U. And so the inverse of the product of the elementary matrices gives you L. And then when you solve AX equals B, you first solve Ly equals B for Y. Using forward substitution, then solve ux equals y for x using back substitution. Okay. So the LDU decomposition is essentially the same thing as the LU decomposition. The only difference is that the U matrix will have 1s on the diagonal because the D takes out the diagonal of the U. So if we do an example of that, in the previous problem, our LU factorization was 1, 0, 0, 0, 1, 0, negative 2, 1, 1 for the L, and then the U was 2, 2, 4, 0, negative 3, 6, 0, 0, negative 1. So this was LU. To find the LDU factorization, you just take the diagonal from U and put it as the diagonal in the matrix D. And 0 is everywhere else. It's just a diagonal matrix. So that's the D matrix. L is still the same, but you have to change U. So U is obtained, the new U is obtained by taking the diagonal and dividing through by the diagonal, or by taking each row and dividing through by the diagonal entry. So the new U matrix it would be dividing the first row by 2, you get 1, 1, 2. And dividing the second row by negative 3, you get 0, 1, negative 2. And dividing the last row by negative 1, you get 0, 0, 1. So if you write A as LDU, then it's 1, 0, 0, 0, 1, 0, negative 2, 1, 1 times the diagonal matrix times the new U. So that's LDU. So if you know how to find the LDU, if you know how to find the LU factorization, then you pretty much know how to find the LDU factorization.
I just need a kind of reference, but I'm gonna get a notes. But you must be really confident first to sit here.
Okay, another factorization is the PA equals LU factorization. And so it's pretty much the same as the LU factorization. You just have to start, just start by swapping one of the rows of your matrix because you have a 0 in a pivot position. So this will apply if 0 is in the pivot position. Meaning like diagonal, upper left or something. Any entry that you would usually need to reduce the matrix to upper triangular, if that's a 0, you have to do a PA equals LU factorization instead of LU. So an example would be if A is this matrix. So the way I would want to start is by reducing this 1 to a 0 and this 2 to a 0, but I would need to use the first entry in order to do that, but it's a 0. So you can't do that, which means you have to swap the first 2 rows or the first and the third row. Swap row 1 with another row. So the matrix that does that is the matrix you get by swapping row 1. So if I want to say swap row 1 and row 2, Say I want to swap row 1 and row 2. Well, if you swap row 1 and row 2 of the identity matrix, then you get this matrix, which means this is the matrix that when multiplied on the left of A, swaps the first 2 rows of A. Yes?
What is it called?
It's called a permutation matrix. So that means that P times A, if you multiply these two matrices together, it would just have the effect of swapping the first 2 rows, and you would end up with this. And so from here on, you can proceed as usual and just find the usual LU factorization of this new matrix PA, like we did before. So like you would do row 3 minus, you would do row 3 minus 2 row 1 using this matrix. And then PA would turn into this. We're eliminating the 2 here. And then you would do row, we're eliminating the negative 2, so we would do row 3 plus 2 row 2, which has the effect of getting rid of that negative 2, and this 3 is just a 3 still, or wait a minute, nope, the 3 becomes a 7. So E32 in this case is the matrix (1, 0, 0, 2, 1, 0, 0, 0, 1). No, it should be a 2 right here. Because I'm doing row 3 plus 2, row 2. So this is the U matrix. We can write L as E32 inverse times E31 inverse, which would be this product. Which if you multiply it out, it would give you this. So that's the L. And so our PA equals LU.
Would that also be E31 inverse on the left?
Let's see. E31 inverse on the left. Yes. Yeah, because I did E31 first. Thank you. So these 2 matrices would have a 2 here and negative 2 here. Which means, yeah, so the product is still the same. Yeah, okay, so then PA is LU, looks like this. Okay, so the last factorization is the LDL Transpose factorization, which we do to a symmetric matrix. So we need to talk about what a symmetric matrix is. And in order to talk about what a symmetric matrix is, we need to talk about the transpose of a matrix. So if you say, if A is any m by n matrix, then A transpose is an n by m matrix, n by m matrix, whose columns are the rows of A. So basically, to get A transpose, you change the rows into columns and the columns into rows. So the rows of A transpose are the columns of A, and then the columns of A transpose are the rows of A. So an example would be if A is this matrix, 1, 2, 0, 2, 4, 1, which is a 3 by 2 matrix, then A transpose, well, it just takes the first column, 1, 2, 0, and makes it the first row. So 1, 2, 0 is the first row, and then the second column becomes the second row. So 2, 4, 1 for the second row, and that's a 2 by 3 matrix. Another example would be A is the matrix 1, 2, 3, 4, 5, 6, 7, 8, 9. Then A transpose is the matrix you get by writing 1, 2, 3 as the first column, 4, 5, 6 as the second column, 7, 8, 9 as the third column. So in this case, A is a 3 by 3, so A transpose is a 3 by 3. So for a square matrix, you can notice that the diagonal doesn't change when you transpose the matrix. And in this square matrix, the off-diagonal entries just get swapped. So the 6 and the 8 got swapped, the 2 and the 4 got swapped, and the 7 and the 3 got swapped. So for a square matrix, another way to think about it is just reflecting across the diagonal of the matrix. Okay, so we know what a transpose is. So a symmetric matrix is, or let me say A, matrix A. So I'll say matrix A. A is symmetric if A is equal to its own transpose. So its columns are the same as its rows, and if you reflect it across its diagonal, it doesn't change. So note if A is m by n, then A transpose is n by m. So if they're equal, if A is equal to its transpose, if A is symmetric and it's m by n, then m has to be equal to n, and n has to be equal to m, so A is actually a square matrix. So that means that symmetric matrices always have to be square. So that's a fact. So some examples of a symmetric matrix would be this thing. So it's symmetric because these off-diagonal entries are just the same thing. If you reflect it across the diagonal, it doesn't change. So that's what a symmetric matrix looks like. A 2 by 2 case would be these off-diagonal entries are the same These are symmetric matrices. So the final factorization, the LDLT transpose factorization, is just the LDU factorization, but for a symmetric matrix. Is the LDU factorization let's say A equals LDU, LDT factorization is the LDU factorization when A is symmetric. So it's a special factorization we do for symmetric matrices. So why does the LDU factorization become the LDL transpose factorization? Well, let's suppose A is symmetric. So A is A transpose. And say that A equals LDU is the LDU factorization. Then if you transpose both sides, and if you note that the transpose of a product of matrices is the product of the transposes in the reverse order. So this is U transpose, D transpose, L transpose. But A is symmetric, so this is just equal to A, which is LDU. So U transpose is the same as L. And D, well, D is symmetric, so these are definitely the same. And U is the same as L transpose. So that means that U equals L transpose, so A equals LDU becomes LDL transpose. Or you could write it as U transpose DU. But we always write it as LDL transpose. So let's do an example where we find the LDL transpose factorization of a matrix. Okay, so for example, you take this matrix. So A is symmetric, so we can do the LDL transpose factorization. You do it the same way you do the LDU factorization. So you reduce the matrix to upper triangular. We can start by reducing that 2 to a 0. So we can do row 2, minus 2, row 1. In this case, I'm not going to bother writing down the elementary matrices because the lower triangular matrix will just end up being the inverse, the transpose of the upper triangular matrix once we factor out the diagonal. So we don't need to care about the row operations so much, the elementary matrices. So then we want this 3 to be a 0, so we'll do row 3 minus 3, row 1. 0, negative 6. 1 minus 9 gives you negative 8. And then we can reduce this 6 to a 0, negative 6 to a 0 by doing row 3 minus 3, row 2. 0, negative 2, 6, 0, 0, negative 8 minus 3 times negative 6 gives you 16. No, 10. Right, 10. Okay. So this is the U matrix. L is, well, first we have to factor out, so I'll call this U prime because it's not the U that we want for the decomposition. We have to factor out the diagonal first. So D is just the diagonal of this matrix. So 1, -2, 10 on the diagonal, which means that U is the matrix you get by factoring out the diagonal of U prime. So that's U. Well, I already wrote it. Okay, so that's U. And L is U transpose. So L is just the transpose. So our LDL transpose factorization looks like this. So that's the LDLT transpose factorization. Any questions about any of those factorizations? Pretty straightforward stuff. I want to mention some properties of symmetric matrices since we talked about symmetric matrices. So I mentioned one of them already. They're square. Yes. And I mentioned another one as well. If you transpose a product of two matrices, well, this isn't a product. This isn't a property of symmetric matrices. It's just a property of transpose. Let me write /transpose. Symmetric matrices are square. If A and B are symmetric, then A times B is symmetric. Because if you transpose AB, then that's B transpose A transpose. But since B and A are symmetric, this is BA, which is not AB. Okay, so can we find two matrices that are symmetric whose product is not symmetric? Let's try that. So let's think like this. That's gonna swap the rows. So I might as well just do that. And B is, let's say B is
Can I give you a matrix? 3.
3.
7.
7,
7.
7,
3.
3.
Where is your 3?
That's gonna be symmetric though.
You're asking if you're doing A, B, is that
Uh-huh,
symmetric?
right.
So aren't you gonna multiply A and B together to see if it's
And it's gonna be symmetric. I want two symmetric matrices whose product is not symmetric. Is that possible? Is that possible to do? Let's think. Also, if you do A times B, you're gonna get
Well, if you do BA and transpose that, then don't you just get A transpose B transpose, which equals to A times B, so therefore AB is symmetric?
No.
Yes, yes, you do.
no, because AB transpose is B transpose A transpose, not
No, I'm
not
saying
trans-
BA transpose.
BA transpose. That's A transpose B transpose,
Which is just
which is
AB,
AB.
which means AB symmetric.
Is that what that means? No, because that's because BA transpose is not equal to AB transpose. Yeah, being symmetric means it's equal to its own transpose.
Okay.
Okay, but this is a counterexample because if you say A is 0, 1, 1, 0, and B is 1, 2, 2, 4, B is symmetric, A is symmetric. But when you multiply these two together, this matrix is not symmetric. So product of two symmetric matrices is not necessarily symmetric. Does not imply AB symmetric. Okay, figure that one out.
But BA symmetric.
No. Okay, symmetric matrices not necessarily invertible. And invertible does not necessarily imply symmetric either. So properties of transpose are, we've talked about this one. When you transpose a product of two matrices, you have to swap the order. Another property is when you sum two matrices together and take their transpose. It's the same as summing up the transposes. Another fact is if your matrix is invertible, then taking the transpose of the inverse is the same as taking the inverse of the transpose. So there's some properties. Another fact, if you take A multiplied by its transpose, this is always symmetric. A transpose A is always symmetric. So we can check that if we take the transpose of A, then using this property up here, this is A transpose times A transpose transpose, and the transpose of the transpose is just A again. So this is A transpose A, so it's symmetric. For the same reason, A times A transpose is also symmetric. So these two matrices are always symmetric. So here's some properties of symmetric matrices and transpose. If you take a permutation matrix, what you get by just swapping some rows of the identity matrix. For example, This one is a permutation matrix, or this one. For any permutation matrix, the inverse of that permutation matrix is the transpose. That's a fact about permutation matrices. Their inverse is their transpose. Okay, I think that's all I wanted to talk about. I think that covers everything you did in lecture, right?